Let's wait for Carl. Not so many researchers according to the building. It's not that good. I'm not interested. It's all that we are.
Also, it's not voluntary, but
I mean, I should be crying on my office at the Spanish elimination in the World Cup.
you were following. I was looking at the.
Hello, everyone. It's time. Let's start our seminar today, FSI Seminar Series, Special Research at UCF. Now, this is the last episode for this semester, and we'll resume next semester. Today's speaker, we have Dr. Anish Roshi from the Arecibo Observatory, with his research with a small radio telescope. A little bit more about our speaker today. Dr. Anish Roshi graduated with an engineering degree in electronics and communication from the University of Kerala, India. In 1989, he joined the Tata Institute of Fundamental Research, National Center for Radio Astrophysics, Pune, as a research associate officer, where he completed his PhD, specializing in radio astronomy, and later appointed as a faculty there. Dr. Roshi received the Jansky postdoctoral fellow at the National Radio Astronomy Observatory, NRAO USA, and in 2010 moved to USA. Since 2018, he's a senior observatory scientist and head for radio astronomy group at the Arecibo Observatory. Dr. Roshi has an active research interest in astronomy with primary focus on galactic interstellar medium, molecular cloud formation, and massive star formation using radio recombination lines, RRLs. Time is yours, so let's take it.
Thank you, Dhaka, and thank you for inviting. I will talk about the research with a small telescope. When I say small telescope, it's essentially the 12-meter telescope at Arecibo. And instead of giving the title as science with a small telescope, I have put research with small telescope, basically because I have interest both in doing science with that telescope as well as doing technology research with that telescope. So that's why I put the title that way. And those are my collaborators for the science part today I'm going to talk about, and the major collaborators. So first I will give you a background of why we started using this 12-meter telescope. And then I will go into talk about my research interest. Today I will focus on the research interest on galactic interstellar medium, specifically focusing on molecular cloud formation and helium ionization issues. Then I will connect my 12-meter telescope investigation with these two research topics, and later talk briefly about the technology research we want to do with the 12-meter telescope. And I will end with a future planned observations with the 12-meter telescope, but there are other uncertainties now. So to start with, Arecibo hosted the largest radio telescope in the world, the 305-meter telescope, which collapsed in December 2020. So after that, we resurrected a smaller telescope which was owned by Arecibo itself. So this telescope was installed sometime in 2012, and it was not extensively used. The primary reason this was bought by Arecibo was to use it along with the 305-meter dish for a specific experiment called the Very Long Baseline Interferometer. But after the initial testing and doing some fringe testing for the Very Long Baseline Interferometer, this was not used extensively and it was just lying there. So it is a fully steerable telescope, not like the Arecibo dish, where the dish was not rotatable. So the sky coverage was limited, but this has an extensive sky coverage. The elevation goes from 5 degrees all the way to 90 degrees, and in azimuth it can rotate the 360 degrees. But the diameter of the telescope is small, something like 12 meters. And the surface RMS is good enough to go up to, initially when it was commissioned, it could go up to something like 30 gigahertz or so. But now we have to check again up to what frequency it can go. So this telescope came with the room temperature receivers, which are not ideal for radio astronomy applications because those are very noisy. So there were 2 receivers, S and X band. S is about 2 gigahertz and X is about 8 to 9 gigahertz. And after the collapse, what we did is we took the output of this, connected to the 305 meter systems IFs, and started using the backends for that telescope. The backends which were used with the 305 meter telescope. Okay, and the main most of the things I'm going to talk about is only using the Mach spectrometer. It's a spectrometer which measures the spectrum of radio signals received by this 12-meter telescope. As I said, the receivers are room temperature receivers, so the system temperatures are very high. That is essentially gives a measure of how much, what is the noise produced by the system itself. Typically, nowadays, if you for a very good receiver, you get a factor of 3 better than these values. Okay. And of course, the gain of the system, that is when you observe a 1 Jansky source, how much is the power increase at the output of the telescope? That is very small because of the size of the telescope is only 12 meters. For example, if you take the 1 Jansky source and use the 305 meter telescope, you will get a 8 Kelvin increase in the noise at the output of the telescope. But for this, you will get only 40 millikelvin. So you have to live with that. Yeah, so you have to be very careful in designing experiments with this. If you are looking for points or sensitivity, this is not an ideal telescope. But if you can have other signs which can be done, which this smaller telescope will be very, very useful. And the integration of this system with the rest of the backends happened sometime in late 2021, and we started resumed radio astronomy observation in January 2022. And all these things happened because of the engineering team at Arecibo. So I just want to put the acknowledgement there. And currently, two major observations are going on. One is the solar monitoring observation. This is done by P.K. Manoharan, and I hope he may be visiting sometime here and giving the talk. So I'm not going to the details of this. The other very good work which is going on is by Ben Pereira, and he is essentially monitoring pulsars, something like 12 pulsars, and also he is looking for fast radio-based detection with this, and he has already detected one from a repeating fast radio burst. Again, I am not going into the details of this, and I hope Ben will one day come here and give a talk.
One of our semester.
Sorry?
One of you per semester.
But he can come whenever he wants.
Sorry? He can come. So although we started these observations with the existing receivers, we also got funds from NSF to upgrade the front end to build a cooled receiver. So what we decided is, instead of maximizing the usage of this, it is better to go for a broadband receiver, because there's only one feed that can be put at the focus of this telescope. So we decided to go for a very broadband receiver, starting from 2.5 gigahertz all the way to 14 gigahertz. And this is the horn, and this horn plus the amplifier will be cooled inside this cryostat. This is the complete assembly with the horn. There will be a window through which radio waves can go in, but the horn itself, horn as well as the amplifiers will be completely cooled. And the expected noise performance is about a factor of 3.5 better than the current system. And the good news is that the front end is completed and delivered yesterday to Arecibo.
Oh, it came.
Sorry?
Yay, it came.
Yeah.
Very nice.
And this is a measured performance of the front end system at in the lab. From about 2.5 gigahertz to 14 gigahertz, roughly you will get the temperature, receiver temperature around. This is only the receiver from between something like 20 to 30 Kelvin, which is quite good. There will be additional noise which will come in when you put the system on the telescope. So typically about 35 to 40 you will get it on the telescope. That's what we are expecting. And initially the cryo system will be available with the MOX spectrometer, which is 7 spectrometers, and you could observe over a bandwidth of about 1 gigahertz anywhere. You can tune a 1 gigahertz band anywhere between 2.5 and 14 gigahertz. And that 1 gigahertz can be broken up into 7 spectral. So that's what we have the system. I mean, that's the system which we are planning to, which we are using for the observation, or the cryo system. We will be soon start the observations once this system has been put on the telescope.
Anish,
Yes.
just one clarification. So this is the instrument that you are going to have. The only one is a spectrograph that observes on a band of 1 gigahertz at 7 different windows.
Yes, within one, at any instant, only 1 gigahertz you can observe, because that is limited by the tuning in this block.
And can those different mobs be tuned to observe at the same window
Yeah, you can.
also?
Yeah, you can do that.
So that you increase the signal to noise maybe or not?
No. So if you take, this is a 1 gigahertz bandwidth, you can break this into 7 spectrometers and place them separately with the 7 spectrometers. Okay. So you can cover the entire 1 gigahertz bandwidth with the 7 spectrometer. Each spectrometer will observe only much smaller than that, about 170 megahertz or so. But what we originally planned was there will be a second fiber link, and there will be 2 1 gigahertz bandwidth, which you can place it at 2 different places in the 2.5 to 14 gigahertz. That will not be available immediately. So that's the background I wanted to give why we are using this 12-meter telescope. So now I will focus on the research part, particularly on the interstellar medium research. As most of you know, the interstellar medium consists of different components. You can have the neutral component, which are probed by the H1 gas, which is essentially the neutral hydrogen. And there is also ionized regions in the interstellar medium. These are ionized by massive stars. Therefore, the H2 region, they are dense ionized gas surrounding the massive stars, or the photons can leak out to very large distances to produce an extended medium with a filling factor, volume filling factor of about 25% or so, which is called the warm ionized medium. In the talk, I will mention this medium as the warm ionized gas or a warm ionized medium. Okay. And there are other components like the molecular gas and the hot ionized medium, which I'm not going to go into the great details today. The main tool I use for research is what is called the radio recombination lines. These are spectral lines like the Balmer series and Lyman series, which are transitions occurring at very low quantum states. But when transitions happens at very high quantum states, like n is equals to principal quantum number 271 and 272, there's an electron making a transition from 271 to 272 to 271. It produces a photon at 325 megahertz. Okay. And that it's designated as H271 alpha. Alpha stands for the change in quantum number as 1. So if you take a typical spectrum, this is a spectrum obtained with the 305 telescope, you will see hydrogen and other elements, spectral lines, because of this transition. And the frequency of the transition is determined by the classical Rydberg's equation. But the Rydberg's constant here depends on what we call as the reduced mass of the electron, which depends on the nuclear mass. So for the different nuclear mass, the rest frequency of the rest frequency of the line will get shifted to higher frequencies when the nuclear mass increases. Okay. So that is the reason in the spectrum, although the transitions are same from the same quantum number, hydrogen and carbon will have two different frequencies, and the shift in frequency in kilometers per second is about 150 kilometers per second. So, and from this spectrum, we can immediately say that this element, the carbon, is not coming from the same region where hydrogen is, because the cosmic abundance of carbon is about 10 to the power of -4, but your line ratios are much smaller than that. So, which means that these two should be coming from two different regions, and typically hydrogen comes from regions where the material is completely ionized, and carbon comes from regions where it is partially ionized. When I say partially ionized, hydrogen will be neutral, but carbon will be ionized. And that happens because carbon has an ionization potential smaller than that of hydrogen. The ionization potential of carbon is about 11.6, but hydrogen is about 13.6 eV. So, so typically when we observe, we will see hydrogen, sometimes helium here between hydrogen and carbon, and then we will see carbon lines. And yeah, I use all these spectral lines for research, and they give very different information because they are anyway coming from different regions. The partially ionized medium, which is probed by the carbon line, can be used to study the molecular cloud formation. So I'll first talk about that, and then later talk about how I am going to use the hydrogen and helium recombination lines to understand the origin of the warm ionized medium, or what essentially ionizes the warm ionized medium. So I mentioned that there are different components in the interstellar medium, but they are not static. The interstellar medium is quite dynamic. There will be transitions from atomic to molecular form, and then from the molecular clouds, stars forms, and stars ionizes them, and also it ionizes. It gets destroyed in the supernova explosions, and it also ionizes the medium, and from the ionized medium again neutral medium forms, and this cycle keep continuing. Yeah. And one of the and understanding this cycle is very important because that determines the evolution of the galaxy, and also the what type of stars and planets are formed in our galaxy. And one of the least understood part in this cycle is the transition from the hydrogen to molecular cloud formation, and I mean H1 to H2 transition, which is what I am calling as the molecular cloud formation. There are several ideas which people have been proposing for the formation of molecular cloud. One of the ideas is to have shock on a neutral medium. So when you have a shock on a uniform density region and you observe after a few million years, you will see this density contrast. And these density contrast, what is shown in this colors are the density contrast, and the blue ones are higher density regions. And the higher density region, if you look at the phase diagram, it will have lower temperature. Okay. So, and the other possibility which people talk about is you have a uniform cloud and there's a quasi-static contraction of that cloud, which produces the conversion from H1 to H2. Okay. In both cases, you will have a dense, cold H1 region present in this formation process. And that cold H1 regions can be observed using 21 centimeter line, the H1 21 centimeter line. So that is one of the probes you can use for measuring the properties of these dense regions where the molecular formation may be eventually taking place. The second tool that can be used is the carbon recombination lines. So typically, when people observe carbon recombination lines, they observe at lines from dense molecular interface regions with star forming regions. With they are called this photo dissociation regions, and you typically see carbon lines at frequencies greater than about a gigahertz or so. But there's also carbon lines observed at lower frequencies below 1 gigahertz and 300 megahertz and so on. And those lines are coming from the transition region. At least some of them are coming from the transition region from H1 to H2. So the idea which we are exploring is to combine the H1 and these carbon recombination lines in these regions and try to establish or try to understand the formation of H1 to H2 transition. Okay. So people have been observing these carbon lines from various directions, and many of these carbon lines are associated with the H1 absorption. But some about 10 years back, we found that there are carbon lines which are associated with what is called the H1 self-absorbing cloud, which are H1 being absorbed by the H1 emission itself. Okay, so these are cold gas which is embedded in the warm H1 gas. And there are carbon lines which are associated with these H1 self-absorbing region. And these regions are, people have been talking that these regions are regions where the molecular clouds are being formed. Okay. And the interesting thing about the carbon line is that you can observe carbon line in emission at certain frequencies and absorption typically at lower frequencies. This is about 34 megahertz and that is about 325 megahertz. And you can model this line formation to estimate the electron temperature, electron density, and the size of these carbon line forming regions. Now, you can also constrain the properties of this medium just from the line width, because the lower frequencies, when you come to 100 megahertz or below, the radiation and collisions dominates, and that affects the line width. So to understand how it is happening, it essentially comes from the uncertainty principle. When the level depopulation rate increases, the line width increases because it has the inverse relation to the uncertainty relation. And in this depopulation rate, the collisions play a major role, and that collisions are determined by the electron temperature and density, and therefore you can constrain just from the line width the electron temperature and density. And from H1, you could constrain the excitation temperature of the H1 and also the column density, but you cannot exactly pinpoint what the column density and the excitation temperature, but you can put a constraint on this parameter space. But what we are trying to do is combine both H1 and carbon recombination lines and try to see whether we can estimate this molecular cloud formation which is happening inside this cold regions. And we have taken an example cloud, which is the fusion Regal Crutched cloud, which is a famous H1 self-absorbing cloud towards the center of our galaxy. And essentially applied this technique. So basically the technique is this, from the carbon lines, you get the electron temperature, electron density and the line of sight distance. You can put a constraint on the far UV radiation field because if you assume ionization equilibrium, and H1 gives you the excitation temperature of the H1 and the carbon density of the H1. Now, because you know the electron density, you will get a total density of hydrogen in that region because you know the abundance of carbon in that region. And from the H1, if you assume the spin, if you assume the excitation temperature is close to the electron temperature, because they coexist, then you will get the H1 part of this total density. And once you get the H1 part, you can calculate what is the H2, how much molecule is there in that part. And with all these parameters, you can immediately calculate what is the molecule formation rate and molecule dissociation rate. And we did this for this cloud HRC towards the galactic center region. And what we found was that the molecule formation rate is an order of magnitude larger than the dissociation rate. So the cloud is essentially being converted into a molecular cloud, and the time scale for this conversion is about 5 years or so.
And this works only for H2.
This works only for
H2, for the molecular hydrogen.
Yeah. When I say molecular cloud formation is essentially the conversion from H1 to H2.
To H2.
Yes, not any other molecules.
Yeah.
Because we don't have in this model, there's no chemical network that is being put in. That is another thing which will be eventually put into this chemical network.
Thank you.
And this H2 you cannot probe directly because usually CO is used as a proxy to measure the H2 in a molecular cloud. But because the densities of these molecular cloud forming regions are very small, CO cannot be used as a proxy because the CO will not be excited. Okay, so this is a clever way of getting the H2 content by combining carbon and H1. Is a clever way of getting the H2 component indirectly. Okay. And that is what is allowing us to calculate what is the molecular formation rate. So we want to continue this research. So we right now have a large survey going on with the Green Bank telescope. We have been about 1,000 hours to do this survey. And that survey will give you hydrogen, helium, and carbon recombination lines at frequency 325 and 750 megahertz. And there's also a already existing survey which exists at 5 gigahertz of the hydrogen and helium recombination lines. And in addition, what we want to do is to use the 12 meter to look for a molecular transition at 3.3 gigahertz. And the interesting thing about this molecular transition, that is this molecule, the CH radical, is that these CH radicals are present in the molecular cloud forming regions. So you could, if you make a chemical network, you can combine that with this data set, the carbon recombination line and H1 data set, to completely characterize the formation of this molecular cloud. That's what that is the idea of using this 12 meter for these observations. And the interesting thing is the 12 meter, although it is only, I mean, it's 10 times smaller than the Green Bank telescope. The frequency is 10 times larger, therefore they have similar angular resolution. Okay, so that is what I'm interested to do with the carbon lines. Now I will concentrate on the hydrogen recombination lines in the observed data. As I said, the hydrogen lines comes from the fully ionized gas. They are associated either with the star-forming regions, or they can be associated with the very extended cloud, which is essentially the warm ionized medium. So if you look at the star-forming region, there are dense, small size typically of 0.7 associated with very young star-forming regions, and the densities are quite high. That's also evolved these H2 regions later evolved to form compact H2 regions. But apart from these, this is what the famous Orion nebula or other nebula which you H2 regions which you commonly read in or see the pictures of this in the astronomy literature. But what we are interested is not those H2 regions, but there's a diffuse ionized gas which is present throughout the inner galaxy and even beyond the galactic plane, and which is what is called the warm ionized medium. Okay, and the inner region, the medium which is there in the inner region of the galaxy has a density which is about 10 times larger than the warm ionized medium, and therefore these region can be observed in the radio. But this has a emission pressure much smaller than what you encounter close to the galactic plane, and they can be observed only in the H alpha. So, and H alpha cannot probe these regions, only radio can probe these regions because of the extinction in the galactic plane, higher extinction in the galactic plane. So the radio is the best way to study the properties of the denser warm ionized medium present close to the galactic plane. Now, the basic question is what ionizes this warm ionized medium? Typically, it is believed that the massive stars in our galaxy is what is ionizing the warm ionized medium. So if you have stars which is producing a lot of ionizing photons, they ionize the material around that stars, and this gas will have a helium and hydrogen at the cosmic abundance of about 0.1. Okay, but the helium ionization potential is higher than that of hydrogen. So you need higher energy photons to ionize helium. Okay. So now the size of the helium, how much helium gas is ionized compared to how much hydrogen gas is ionized, is depend on this factor called gamma, which is essentially the total available photons for helium ionization and total available photons for hydrogen ionization. So from the basic calculations, you can show that if gamma is greater than 0.2, then the helium and hydrogen the ionizing regions will be overlapping. So it will be like this if gamma is greater than 0.2. And if it is less, it will be something like this. The hydrogen helium will be size of the helium region will be smaller than the hydrogen. Now from the Lyman continuum requirements for the regions which I was showing close to the galactic plane, you can show that the gamma of the stars or star clusters that are producing the ionized medium should be greater than 0.2. This essentially comes from the initial mass function and the properties of the ionizing properties of the stars which are present there. So you can directly test this by observing whether helium is detected wherever hydrogen is detected close to this 0.1 abundance ratio of 0.1. And we have tested this. So we observed with the green band telescope in regions away from the usual dense star forming regions, but at a more diffuse regions. And we found that there is no high helium detected. And the upper limit we get is about 0.02. Okay. And we also did observations close to the very young star forming region, like what is called the interconvex H2 region, but in the diffuse regions close to the ultraconvex H2 region. In the towards the ultraconvex H2 region, you detect helium, but there's no helium detected in the diffuse region, but hydrogen is detected. So this plot essentially summarizes towards star forming regions and compact H2 regions. You see the helium to hydrogen ratio is close to 0.1, close to the cosmic abundance, but in more diffuse regions, particularly in the extended warm ionized medium, you don't see helium ionize. Yeah. So then the question is, what is ionizing the helium? Because as per the expectation, you should see helium ionized. Helium should be ionized. We also checked whether helium is doubly ionized. If it is doubly ionized, then the spectral lines will have a different frequency. So you can look at that, look at those frequencies and see that the helium is doubly ionized, and we didn't see helium doubly ionized. And therefore, we think the helium is neutral in these regions. So then the question is, what then ionizes the warm ionized medium if the stars are not ionizing? So there should be more hydrogen ionizing photons that should be coming from somewhere. And one possibility that has been suggested is the lower mass stars may be producing more hydrogen ionizing photons. But there's no much progress that has been made on estimating this further, but there was only a suggestion. There's another suggestion which is more interesting, is the decay of the dark matter, which produces 14 EV electrons, and which could be adding to the, which could be producing the extended warm ionized medium. And there's also another possibility that the photon spectrum can get modified by the dust in the interstellar medium. So before going into this part, we thought we will check this. And the idea is essentially this: as the photons propagates from the stars to distant regions, the Lyman continuum photons get absorbed by the dust in the interstellar medium, and the absorption is proportional to the cross section of the dust at the two Lyman frequencies, that is the hydrogen ionizing photons and helium ionizing photons. And because these, if sigma h and sigma h are different, then the photon spectrum gets modified as it propagates outward, and that change in the photon spectrum changes this gamma, and therefore the size of the hydrogen and helium regions can change. Okay, and directly by measuring the hydrogen and helium line ratios, we can put a constraint on the ratio of these ionizing cross sections. And from our observations, we estimated the ionizing cross section and compared it with the dust extinction model that people have been using extensively from various infrared observations and other optical observations of extinction. And if we want to explain the observed helium to hydrogen ratio in the interstellar medium, in the warm ionized medium, at the observed level, then the extinction should be something like in this range for the 24.6 EV, which is inconsistent with most of the other observations. So, so we think the dust extinction with the existing model cannot explain the helium to hydrogen ionizing ratio. So that is sort of ruled out from our observations. So to understand this better, we need a better modeling. So this survey data is something which we are going to use for the, yes.
I'm sorry, can I interrupt you?
Yes.
Can you go back one? Just for me to understand this. So what you're saying is the fact that there's dust changes the numbers of photons that are going around, because this dust could just be heating up or something by receiving some So the dust would reduce the amount of available photons
Yes,
to do the ionization.
it gets excited and re-radiate in some other way.
All right, so can you re-explain me, sorry, how do you draw these lines, like what? So, because this is an extinction, I guess, diagram,
Yes, it's an extinction diagram. This
So-
extinction is connected with the absorption cross sections.
right?
So we have a ratio of the cross sections. Suppose if we consider this as the hydrogen cross section at 13.6 eV, then the upper limit on the hydrogen to helium ratio gives what is the value expected at 24.6 eV for that.
And this peak in the dust extinction cross section, that's which molecular, is that a silicon,
Yeah, it is a combination.
SiO,
Yeah,
or what?
they have a combination of this. RV essentially gives the combination of silicon and also the structure of the molecules, the number of, and I think the number of atoms included in the molecules in the dust type.
I thought RB was just how much dust there is, to
No,
be honest, okay.
these various values for the RV is the ratios of the
But
different
you
mixture of
change
the.
the case also,
Yeah.
A, B, B, okay. Okay. So what you're saying in layman's words is if the presence of the dust was the reason why there's not enough photons around, then you would see this absorption cross section at another place. Because it would be absorbing all these photons that you're expecting there, but they're not, they're absorbing photons somewhere else. Is that what you're saying?
Yes, the absorption is not large enough at 24.6
I see.
for
Mhm.
it to explain the observation. Suppose that the simplest way of looking at it, if this peak were shifted here,
Because see, that's, I guess, this is a model, right?
yeah, it's a model which is consistent with a lot of other observations.
Yes, okay. And they never see a shift in their models. They never see a shift. It's always at, what is it, 10.2?
Yeah, somewhere between
Yeah,
13 and
okay,
24.
okay. Thank you. For humoring me.
So the idea is to improve this, to improve the estimate of the ionization requirements and measure better upper limits for HE so that you can rule out other possibilities. And again, the GPT observation, which has the hydrogen and helium, we can use it for this purpose. But I'm also trying to see whether the 12 meter can be used to put additional constraint on the properties of this ionized gas just by looking at the continuum emission from this ionized gas. The ionized gas not only produces spectral lines, it also produces continuum emission. Okay. But that is still an exploratory program, whether we can detect to the level at which we can say put a meaningful constraint still has to be demonstrated. So now I will briefly mention the technological research part of the 12 meter telescope. So I showed you the receiver temperature measurements in the lab. But if you actually put the telescope, put the receiver on the telescope, you will start seeing all these additional features which are produced by man-made interference. It's called radio frequency interference. And we have a research program that was started with the University of Puerto Rico. NSF has funded a center called the Center for Advanced Research in Science and Engineering. And the idea is we will use the 12 meter along with a set of reference antenna and build a system so that you could use the reference antenna signals to, the reference antenna essentially picks up signals from the man-made interference. Predominantly, the man-made interference will be picked up by this reference antenna. You use that to cancel out the signals, the RFI picked up by the 12-meter telescope. So this is something which we want to try and see whether it can be used for astronomical observations. So essentially, the 12-meter form a facility for doing this RFI mitigation studies and other engineering applications. Okay. Like if we are developing a low noise amplifier that can be tested along with the 12-meter to see how effective that is for RFI mitigation related stuff. And there's also 12-meter being used for student mentoring project. One of the NSF funded project is called the Encanto. This is a collaboration between UPR, UCF, and the AO. The basic idea is to train undergraduate students for, basically research training. And we right now have 9 students working under this program. And most of the work is connected with the 12-meter program, 12-meter research programs. And finally, I want to list a set of projects which we have already thought about to do with the cryogenic receiver. Most of the things which I have listed here are done by the Arecibo scientists itself. In addition, once the cryogenic receiver comes, we will be having applications to we'll be participating in the VLBI experiments with the European network, and there are plans to participate in geodetic VLBI. This is essentially to determine the celestial reference frame, which will be very useful for the rocket launching movie. And there's a set of external science projects. People outside the observatory is also interested to use the 12-meter. But I will stop there because I don't have anything more to say at this point about the 12-meter. Thank you.
All right, thank you. I think let's open up for the questions. So let's give the priority for the online people. Please unmute yourself if you have any questions. All right, looks like.
I have one. I
Okay.
don't know why you all look at me.
Go ahead. I thought you wanted to ask the question.
Okay.
You go ahead and ask.
I will.
Yeah.
I understood. I
That's why
didn't
we're
want
looking
to
at
ask
you.
you question. I said, okay.
That's why we're looking at you.
Okay, so I have one. It's more on the 12-meter as telescope done on your science that I find very interesting. It has taken me back to when I was studying astrophysics. So thank you for that triple time. The 12-meter with the cryogenic receiver. What can it do that GBT or Goldstone or an NRAO cannot do?
Okay, I'm trying to see which is the, okay, let's take okay, let's take this project. This is to be established. The feasibility study is still going on. Suppose if the 12-meter is good for looking for the long-term variability of AGNs. This is a project which needs high cadence observations. Every week or so, you have to keep taking the data over a much longer period, like several years. You may not get GBT to do that sort of any of the bigger telescopes to do that such a So this is a great project for 12-meter.
Okay, long-term change.
So what you're saying though is it's an availability
Yes,
advantage.
yeah.
It's not really a technical.
Yeah, I know. It's typical from also in the optical. Sometimes to have very competitive large telescopes, and you have smaller ones that are not so powerful, but are more available there. So the pressure is lower.
Yeah.
So when you need to do observations like light curves, for example, that you need to observe for a certain amount of hours to really characterize the variation. You will never get that at James Webb telescope or at the GTC that is at the meters, but you can do that with a smaller one.
Yeah.
So that combined with what you can get in others, it's.
So that is an example for the availability, as Julie said. Now let's take this observation, the CH observation. The CH observation is you are going to measure in the interstellar medium with their extended sources. You don't need GBT for that observation because the source is extended. And therefore, if you want to do a large scale survey, so each position, these lines are weak, each position you have to observe about an hour or so. And with a beam of about half a degree or so, if you want to cover the entire galactic plane, it is going to be a highly time consuming project. And GBT is not, one thing is GBT is not required for such a survey, but also that you won't get GBT time for that.
Okay. And the other question would be the technology that CARS is starting to remove the interference from the signal. Would that be applicable to other radio telescopes?
Yeah, the idea for the CARS is it is going to be a facility where you can see it is not an easy problem. The removing mitigation. I mean, implementing. Successfully implementing RFI mitigation is still not proved for radio astronomy.
Yeah.
So you need to develop new algorithms, new technique, new ways of subtracting that. So you can use this 12 meter because of the time availability. You could use this, test it. You can do actual observations with the 12 meter and apply that algorithm and see, make sure that things are working very well. And then you can always take it to another observatory and implement it. So this is like a facility to develop it.
That's some motivation to keep CARS going even after.
Yeah.
Even if there is no plan to install any large telescope at Arecibo. Because this technology you could use export it to other radio telescopes in the US. The third one, if I'm allowed.
Sure.
Sorry, we will come back. I forgot.
And there will not be, as far as I know, in the US, there is no such facility where what do you mean, the ingredients required for developing and testing RFI mitigation exist as a facility where you can go and do research. So this will be in that sense a unique. Yeah, go ahead.
The third was on geolocalization. Is there any of the science that you're doing with the 12 meter that cannot be done with the radio telescopes that are available in the mainland in the US? Like with GBT, because of the location, I mean, because being in the Caribbean. Like reaching out to one part of the sky that you cannot reach with the others.
No, I think sky coverage may be roughly same. But I was wondering what other operation telescopes are there which can do any of these things. The smaller facilities are mostly closed down.
Yeah, smaller ones in the US. There are not so many, really.
Yeah.
Maybe in Canada. I'm not sure.
So they closed down the small facilities?
Yes, many of the haystack, they have closed down the millimeter wave telescope, right?
Why?
Okay. It's the Karma has been closed down. I know the Karma case. The Karma is a millimeter wave observatory facility run by Caltech, and they
Who's funding it?
NSF was funding it. So the decadal survey is set to close down some of those facilities and divert the funds to major research facilities like ALMA. Things. Okay, so what I heard from the Caltech group is that is sort of killing the opportunity for doing small experimental work and moving towards the bigger facility instruments. So they were quite upset about that.
And that came from the community though, if it's in the Decatur survey.
Yeah, it is in the Decatur survey. The Decatur survey recommended that.
Were you in these conversations?
Sorry?
Were you in any of these decadal survey conversations?
No, I was not there directly involved.
Okay. All right. Good.
Okay, I have one slightly theoretical question. You mentioned the dark matter contributing to the hydrogen ions. For some reason, I never heard that phrase before, like dark matter converting into ions. Can you talk a little bit more, or
Not.
does that mean like
Emitting.
dark matter is decreasing and contributing more to the physical mass?
That's a good question. What I said is a dark matter producing hydrogen ionizing photons. So there's something in the dark matter that is decaying. So there are particles which are decaying at some rate, and it is producing something like 14 EV electrons. So this is a theoretical prediction, but it's not clear whether.
Okay,
I mean,
Well, it's a
it is
purely
a.
theoretical prediction. It's not an observation in any way.
Sorry.
It's not an observation.
No, it is not an observation. So if the dark matter is decaying and the decay energy is at 14 eV or so, they have some arguments to say that it is close to 14 eV. In that case, there will be 14 eV photons available to ionize the hydrogen. And then you can work back. I mean, so suppose if we could do better modeling and rule out some of these possibilities, then we can put a strong constraint on what is the decay rate of the dark matter. That's what we are eventually aiming.
I mean, okay. If this theory is.
If the theory is right,
Yeah.
we can rule out
Okay.
that. Rule out or put constraints on the theory.
Okay. So I have a question about dust again.
Sorry?
Dust.
Yeah.
So,
The dust here.
yeah. So, are there any? Not really with its interaction with the, the ionizing photons, but more. Are there any absorption or emission lines of dust within the range that could be captured by the 12-meter telescope? Could you do dust science basically?
No, these frequencies, it's mostly continuum. So there is the dust emission will have a small tail at close to 14 gigahertz, but it's very weak. And the thermal emission and non-thermal emission and CMB will be dominating over dust at the frequency. They are dust continuum emission.
And how about
Spectral lines.
missing emission because of the dust being there? If you're observing a molecular cloud, you're not getting enough photons at that wavelength because dust is there, let's say.
What you're saying is then dust is optically thick.
Yes.
I'm not sure.
At these wavelengths, obviously, yeah. Would have to be big dust, I guess.
And you would need also
Yeah.
a method of reference where you can really see how much of that molecule is there.
Yeah.
To know that here you are missing that. Because
Well-
dust is absorbed.
Yeah, but let's say you have a good idea of what the continuum looks like. And then boom, there's a region where, I don't know.
You know,
But I actually,
get
yeah,
what
I
you say,
take
yeah.
that back. These have to be pretty big dust, yeah, okay.
Yeah, dust emission is optically thick at these frequencies because you will essentially see the black body, the Rayleigh part of the black body from the dust. But your question is that is the emission in the individual dust is optically thick, like the. But what we are asking is whether the column density of the dust is large enough to produce enough absorption of other radiation coming.
To be detected.
That I'm not sure about. I don't.
Okay, I'm just wondering if any dust science could be done.
Yeah.
With the 12 meter.
Yeah.
Will it take long?
Yes,
Okay.
It was nice seeing you.
Okay, let's thank our speaker again.
I have one more question for you. This is just